All right, so in this chapter, we'll talk about capacitors. So let me start off by showing you a app. All right. So here, this is what is called a parallel plate capacitor. And I'll show you what's going on. So here's a battery. What is a battery? What is a battery? It's a store of chemical energy. Okay. So when you buy a battery, what you're doing is you're buying a packet of energy stored in a certain way. Okay. So now what we'll do is, so I'll turn on the battery. Right now this has 0 volts. Okay. So here's what happened. All that happened very fast. So this battery was a 1.5 volt battery. When you connect the battery, what the battery does is it establishes an electric field in these wires. Okay. And the electric fields make the electrons move in this direction. So the electric field direction is in this direction, and the electrons will move in this direction. Okay, so electrons move from here to there. Electrons collect here, and these electrons will repel the electrons from here, and so this plate gets positively charged. Okay, and all that happened very fast. Okay. And when the charges are collected, there's an electric field established. Okay. So why did this stop now? Why isn't charge continuously flowing and collecting till the battery dies? So charges flow till this capacitor, the voltage across the capacitor equals this 1.5 volts. Okay. When the voltage across this equals that voltage, then what has happened is the electric field in this wire has gone to 0, and that's why charge flow has stopped to 0. Okay. So again, when there's no charge on the capacitor, there's no energy stored in the capacitor. Okay. So now what we have done is, I'm going to charge it again. Now I have charged the capacitor, meaning I've stored energy in the capacitor. So what did I do? I just transferred energy from here to there. Okay. Why did I do that? Why did I move the cheese from here to there? You guys understand? Why not leave it just there? Yeah, this guy can release it. This guy can release the energy very fast. This guy can only release energy very slowly. So you guys have all used a flash camera. Okay, so in a flash camera, you take a flash camera picture, and then the bulb in the camera, the amber bulb blinks. What's happening is this guy is charging the capacitor, and he takes a long time to charge. Okay? Now once this is charged, here's what you can do. You can discharge this energy very fast through this bulb. Okay? And the rate at which you discharge can be controlled, okay, as fast as you want. You can discharge it through the bulb. This was a flash bulb. This could be heart, somebody's heart. You could jump start the heart. Okay, that's a defibrillator. Okay? And in a pacemaker, the capacitor gets charged, and then periodically you send a pulse to, how often do you send a pulse? 60 times a minute or 70 times a minute through a person's heart to make sure it beats properly. Okay? So you have a lot of applications. Anyway, so you store energy is stored in a capacitor whenever you want to release it fast. Okay? So transfer of energy from here to there is a slow process, and then you can release the energy very fast. Okay? You guys understand? Okay. How much energy is stored in this capacitor right now? None. Yeah, okay. So when there's no charge in the capacitor, no energy is stored. Okay. All right, so that's what we're going to learn. Again, these are very useful devices. You use them all the time. Okay. So all your electronics have thousands of capacitors in them, okay? So, all right, so we'll learn about all this capacitance. That's how much, how large is the capacitance is the value of the capacitor, okay? And then we'll see how to combine capacitors. We'll see how much energy is stored in a charged capacitor, okay? And we'll come to dielectrics. Okay. So capacitors are also used in tuning circuits. Okay. So here is the tuning circuit. Okay, so this is what is called an inductor, which you'll learn about in maybe 4 or 5 chapters. This is a capacitor. Capacitor is denoted by C. Okay, and just like this mass attached to a spring, it has a natural frequency of oscillation. The frequency of oscillation is 1 over 2 pi or K over M. Okay. K is the spring constant, M is the mass attached. So this likes to oscillate at that frequency. Okay. Just like that, if you charge this capacitor, it will oscillate. The current will flow back and forth. And it has a frequency of oscillation. The angular frequency is given by this. And like I said, you'll learn this 4 chapters from now. Okay. So here's the deal. This is how all wireless devices talk. Do you have any wireless device? I'm sorry? Your phones, your radios. Every wireless device, at the heart of every wireless device is this tuning circuit. Okay, so what it is, so this device, so like I said, if you charge this capacitor, if you charge this capacitor, the current would oscillate back and forth. Okay, just like this mass would oscillate back and forth. And the frequency at which it would oscillate is that. Okay, so now here's the deal. So let's say there's several signals in this room. This is a frequency of 100 megahertz. Here's a frequency of 102 megahertz. Here's a frequency of 103 megahertz, 104 megahertz. Okay, so how do you pick up? So this is the signal you want to pick up. How do you pick up this signal and not pick up these 2 signals? So right now in this room, there's at least 10 radio stations from Orlando trying to get your attention. How do you pick up the one you want to listen to? Do you guys understand the problem? So there's a signal everywhere. I mean, there's a signal of all frequency. So what you do is, if you want to pick up this thing, you adjust your capacitor such that the frequency of this matches the signal you want to pick up. And that will send the largest current here. All these guys will induce a small current. That's resonance. Okay, so that's how you use them. Okay. So a capacitor is at the heart of every tuning circuit. So there are trillions and trillions of these guys because we use wireless devices all over the place. Okay? So these wireless devices are at the heart of this tuning circuit is at the heart of so many things that you use. Okay, so again, I will draw that tuning circuit again. So here's a capacitor. Here's an inductor. Okay. And the frequency of oscillation, this is angular frequency is omega by C. I mean C, L by LC. Okay. And here is the antenna sticking out, listening for the signal, to pick up the signal. Okay. So this, you cannot live without this these days. Okay. All right. So capacitors are used in tuning receivers as filters in power supplies and all, and energy and charge storing devices among other things. Okay, so you store energy in capacitors, and you can release that fast. Okay, so capacitors can store electrical energy just like batteries, except capacitors can discharge their energy much faster. So that's the key. Okay. So for instance, you saw the flash bulb. So you saw this flash bulb. Okay, so you charge this capacitor and you discharge it through that flash bulb. Okay, so here are the numbers on the flash bulb. Okay, so in your cameras, capacitors used to light flash bulb. You can store 20 joules of energy in the capacitor. These are just typical numbers, which is 20 kilowatts for 1 millisecond. What that number means is the following. 20 kilowatts, that's 200 times 100 watts times 1 milliseconds. Okay, so let me show you the calculation. 100 watts, watts is joules per second, and 1 millisecond is 10 minus 3 seconds. Okay, so the second will cancel, that will kill, and so this is 20 joules. Okay, so what this number tells you is the following. You store 20 joules of energy on this capacitor, and when you discharge it through this bulb, what that is telling you is this following. For 1 millisecond, that bulb lit like 200 100-watt bulbs for 1 millisecond. And what did that do to you? If this room was entirely dark, I could still take a picture. It'll turn night into day, okay, in this room. And that does it for 1 millisecond, okay? All right, so to make a capacitor, all you need is 2 pieces of metal. Any 2 pieces of metal are good, okay? And then if you connect the 2 pieces of metal to a battery like this, okay, what will happen? Electrons will flow from here, and these electrons will repel these electrons, so you'll have equal and opposite charges on these 2 pieces of metal. Yep. So any 2 pieces of metal can be made into capacitors. 2 conductors isolated from each other and from the surrounding form a capacitor. So when a capacitor is charged by connecting to a battery, equal and opposite charges reside on them. Okay. And since these are metal, you've learned in the previous chapter, they are equipotential surfaces. Okay? And how much charge flows till the voltage across the capacitor equals the voltage of the battery. Okay? So if this is a 10-volt battery, the capacitors will be charged to 10 volts. Okay? All right, so this is a common configuration. This is a parallel plate capacitor. You take 2 metal plates, okay? And if you connect them to a battery, you see that this has a negative charge and that has a positive charge. And what this shows you is the charges reside on the inner surface here, okay? So the negative charges are sitting there and the positive charges are sitting there. The capacitance of a capacitor is how much charge can it hold per volt. Okay, so if you connect this to, so how much charge it can hold per volt. And this combination, charge is measured in coulombs, volts in volts, and that combination is called a farad, after Mr. Farad, who studied this kind of stuff. Yeah. 1 farad is a very large capacitor. So in your phones you have capacitors that are picofarads, microfarads, nanofarads, and stuff like that. Okay, a billionth of a farad. A farad is a large capacitor. Okay, So in applications, you use microfarads and picofarads. Here's the electrical symbol for a capacitor. Here's the electrical symbol for a resistor. Here's that inductor that I talked about, okay? So these two are the ingredients for a tuning circuit again. Let me draw this tuning circuit again. So this is a very important part of your life, okay? That guy is at the heart of every wireless device, okay? So this is a switch and so on. This is an AC source. Here's a battery. The longer line is the positive terminal, okay? And these guys, they're old-time devices. Well, this is a voltmeter. You'll use the voltmeter and ammeter, okay? A galvanometer, you don't use that anymore, okay? All right, so charging a capacitor. So here's a capacitor, and this is the same circuit. This is the circuit that I showed you there, okay? Okay, so this circuit is what's drawn there. So here's what happens. So here's a battery. When you close this switch, the battery establishes an electric field in this wire, okay? And the electric field will be like so. The electric field will have that direction, okay? And what happens is electrons flow from here to there and collect there, and then these will repel electrons, which will come over here. And once the voltage on the capacitor equals that, this electric field has gone to zero, and no more charges flow. Okay, so that's the charging process. So charges flow into capacitor plates till their potential difference equals the terminal voltage of the battery. Electric field at this point in the wire goes to zero. Okay. So now you have transferred energy from here to there. Okay. And then what do you do with the energy, with that energy? You could light this flash bulb, you could jumpstart somebody's heart, you could send a periodic signal once every second in a defibrillator. You're, in a pacemaker, you're sending a signal to somebody's heart to make it beat regularly. That's what a pacemaker does. Okay? All right, so this is a parallel plate capacitor. You can take any two metal plates, okay, and separate them. And that's a parallel plate capacitor. And if you charge it, you're storing energy in it. Okay. Now again, the capacitance is how much charge can it hold per volt. Okay. Well, here's a formula for the capacitor in terms of the dimensions of this parallel plate capacitor. Okay. So A is the area of the plate, and D is the distance between the plates. Okay. You will learn larger the capacitance, more energy you can store. Okay, so we're always looking for ways of making capacitors large. Okay, large capacitor. So how could you increase the capacitance? By increasing the area of the plate or decreasing the separation between them. Okay, so you can do that, so we'll see how to do this. Epsilon naught is called the permittivity of free space. Permittivity of free space, okay, which is a constant. All right, so this is a parallel plate capacitor. Okay. So you can take two aluminum foil, sheets of aluminum foil, and make a parallel plate capacitor. Yeah. Here's a cylindrical capacitor. Okay, so here's a central conductor and a shell around that conductor. Okay, And the capacitance, if you have a capacitor in this configuration of length L, the capacitance is given by the length divided by 2 times the Coulomb's constant natural log of this radius divided by that radius, log of B over A. Okay? So coaxial cables have capacitance associated with them. Okay? So this is a cylindrical capacitor. Okay? So again, now what we're doing is in these two formula, what we're giving you is the formula for the capacitance in terms of the geometry. Okay? So here's another formula of the capacitance in terms of geometry. Okay, you already know why you're using capacitors. You're using capacitors to when you have to release energy fast, and so sometimes, and also to tune circuits and stuff like that, in tuning circuits and stuff like that. Okay, so here's a spherical capacitor. If you have a spherical metal and inside a spherical metal shell, these would be these would form capacitors, and the capacitance is given by that. A is the radius of the inner shell, B is the radius of the outer shell, and there's the value of the capacitance. Now, if you make B go to infinity, meaning you just have the inner shell, if you make B go to infinity, this expression goes to A B times K E B over 1 minus A over B. So in the limit B going to infinity, that cancels, this term goes to 0, and that the capacitance just becomes A over KE, okay, which is that. So the capacitance of just a spherical piece of metal is, the capacitance is A over KE. Okay. Okay, what this shows you is the following. Okay, now again, in many circuits you'll find that you use several capacitors. Okay. So here's what is called a parallel combination. So this capacitor is connected to the battery and that's connected to the battery. So here's the way to write using electrical symbols. So here's this capacitor connected to the battery. This capacitor is connected to the battery. So when you have a parallel connection like this, they both get charged to the same voltage as the battery voltage. Okay. What you want to know is what is the equivalent capacitance for these two capacitors? What single capacitor can you replace these two capacitors with? And the equivalent capacitance when you have parallel combination is just the sum. Okay. So if you have a bunch of parallel capacitors connected, in parallel, the equivalent capacitance is just the sum of them. Okay. So what this is telling you is if you have a bunch of small capacitors and you want a large capacitance, you just connect them in parallel. Okay. So that's how you get a bigger capacitor. Here is what is called a series combination. Okay. Now, so let's say you have a bunch of capacitors, and what you want is a smaller capacitance. Okay, so for instance, you have a 5 microfarad, 10 microfarad, 15 microfarad, and you wanted something smaller. Then you would connect them in series, and the equivalent capacitance, it turns out, will be less than any one of them. Okay? And the value of the equivalent capacitance is given by that. Okay. Now here's the properties. Okay. So when you connect them in series like that. See, electrons flow from here to there. What do these electrons do? They repel. If 10 electrons flow here, they'll repel 10 electrons. 10 electrons will flow here. These guys will repel 10 electrons. and then 10 electrons will go from here to there. So you see, when you connect capacitors in series, they all have the same charge. Okay? In a parallel combination, they have the same voltage. In a series combination, they have the same charge. Okay? So the charge are the same, and in a parallel combination, the voltage is the same. Okay? And also, the voltages will be such that the voltage across 1 plus voltage across 2 plus voltage across 3 will add up to the battery voltage. And the equivalent capacitance is 1 over the equivalent capacitance is 1 over C1 plus 1 over C2 plus 1 over C3. Okay? And it turns out that the equivalent capacitance is smaller than the smallest one. Okay. So, when do you do parallel combination? When you want a bigger capacitor. When do you do a series capacitance? When you want a smaller capacitor. Yeah, than anything you have. All right. So often in circuits you'll see a jumble of capacitors, and you will want to find what is the equivalent value of the capacitor. So what you do is you reduce them step at a time. So when you find a parallel combination, you just add them, okay? Reduce it to that. Okay, now this is a series combination, so you add them, you do the series addition, that's reduced to that. Okay, this was a parallel combination, that got reduced to that. Okay. And these series combination got reduced to that, these series. And now this is a parallel combination which got reduced to that. Okay. So no matter how they're connected, well, again, you can reduce it to a single capacitance. Okay. Okay. Is there any energy stored in that capacitor? No. Okay. Now there's energy stored in the capacitor. Okay. So the question is, how much energy is stored in this capacitor? Okay. The amount of energy stored in the capacitor is 1/2 times the capacitance times the voltage it's been charged to. Voltage squared. Okay, so 1/2 CV squared. That's how much energy is stored in the capacitor. Okay. So the higher the voltage you charge it to, the more energy you've stored. The greater the value of the capacitance, the greater the amount of energy you can store in it. Okay. All right. So we said greater the voltage you charge the capacitor to, greater the energy is stored. Okay. What prevents you to charging it from higher and higher voltage? I'm sorry? Okay, so I want to store as much energy as possible. So the higher the voltage I charge it to, the more energy I can store it. What prevents me from going higher and higher voltage? I'm sorry? Well, Elon Musk is my friend, so. What prevents me from? No, I mean, let's.
So if you had a bigger battery or
Higher voltage battery.
what would stop you from?
Right.
Would it explode?
Discharge lightning.
Very
Yeah.
good.
That's like,
See, that's the limiting factor. Okay. So see, there the limiting factor is you can make this electric field only so strong. If it's air-filled, what is the maximum the electric field can go? 3 million volt per meter, okay? And if you charge it any greater than that, that'll discharge through lightning. All the energy stored will just go away, poof.
So it wouldn't explode?
It won't explode.
Okay.
You'll just have sparks flying and, things burn.
Would that be considered like a short?
Yeah, that's a short,
Okay.
okay? So that's the deal. Okay, you want to store a lot of energy. So for instance, so what do you do? Okay, now here's another problem. Okay, so this is a metal plate. This is a metal plate. That's charged positive. There's charged negative. So this is being attracted by that, right? What's preventing them from coming together? Do you see anything in there? Why aren't they collapsing and attracting each other and shorting? Right?
Sound right.
What?
I said, I don't want to be wrong.
Go ahead. I mean, it's a very simple answer. So of course you stick a piece of rubber in there. Okay, that's called a dielectric. Okay. So here you stick a piece of rubber in between them. Okay. So in fact, so this does multiple purposes. Okay, so it prevents them from shorting, but it also allows you to charge it to a higher voltage. Okay, so here's what a dielectric will do. So dielectric provides increased capacitance. It increases the capacitance of the capacitor, increased maximum operating voltage, and mechanical support. Okay. So did you guys understand that? Okay. All right. All right, so again, here's the energy stored in the capacitance. Okay. Now here's another way of looking at it. Okay. So when you charge the capacitor, you created an electric field in there. Okay. So there's multiple ways of looking at this. So when you charge the capacitor, what are these guys doing? The positive charge wants to attract the negative charge, right? So if you're holding them apart, it's like you're holding a stretched spring apart. Okay. So you're holding a stretched spring apart, and that's storing energy. So that's storing potential energy. Here's another way to look at it. So when you charge this thing, you create an electric field, and you've stored energy in the electric field. So when the capacitor was uncharged, the electric field was zero, and there was no stored energy. So anytime you create an electric or magnetic field, you're storing energy in the field. Okay? And what this formula tells you is, this goes through the derivation, this tells you how much energy you have stored in the electric field per unit volume. That's what this is. Okay? So this is energy stored in the electric field per unit volume. Okay. And you'll see a similar formula when we start talking about magnetic fields. When you create magnetic fields, okay, by passing currents, you'll see you can store energy in magnetic fields as well. And when you get a radio signal, what you're getting is an electromagnetic wave, a wave that has both electric and magnetic field, and that's bringing you energy. Okay? So you are storing energy that in the electric field that you created. So what are dielectrics? Dielectrics, they're insulators, okay? And so a dielectric is a non-conducting material such as rubber, glass, mineral oil, etc. Okay. And so for a parallel plate capacitor, that's the capacitance for an air-filled capacitance. And this is called the dielectric constant. With the dielectric present, the capacitance increases. So this is the dielectric constant of the material. Okay, so it's doing several things now. This is preventing the positive and negative charges, plates from coming together. It's letting you charge the capacitors to a higher voltage and so on. Okay, so when you had an air-filled capacitor, there was a maximum voltage you can charge it to. Why? Because you could have lightning there. Okay, now I've filled this with rubber. Now can I charge it to greater and greater voltages? Is there any limit? You can have lightning through anything. There's lightning through plexiglass. Okay? So this gives you the dielectric strength, meaning at what electric fields that material will become conducting. So you already remember the number for air, 3 million volts per meter. Okay. Through Teflon, it's 60 million volts per meter. So you can fill your capacitor with Teflon, and you could charge it up to the electric field's strength it can sustain is 60 million volts per meter. Beyond that point, it'll short. Okay, so that's what this dielectric strength is. Okay, above these fields, that material will become conductive. Yeah. Did you guys understand that? All right. So dielectrics are materials. Dielectrics are molecules with permanent dipole moment or molecules in which a dipole can be induced. So here, if you put this dielectric between capacitor plates, and there's the field in the capacitor between the capacitor plates, what it does is it will induce a dipole moment in those molecules, and those molecules will create a net field like this. Okay, this is the induced field, and so the net field is decreased between the plates. This is the plate field without the dielectric. This is the induced field, and so with the dielectric, the total field is this minus this. Okay, so that's how come with the dielectric present you can charge it to a higher voltage. Okay. So you want to know this phrase, these words. Dielectric strength means the maximum electric field that can exist in a dielectric before it breaks down. What do you mean by breaking down? Right. When does lightning happen? When this electric field starts ripping off electrons from those materials. Okay, that's when lightning happens. So here shown is the dielectric breakdown of a block of plexiglass. Okay, so what happened here? This was a parallel plate capacitor. This was a parallel plate capacitor. You put a block of plexiglass here, and you charged it you put too much charge there, and you had lightning go through. Okay? The electric field inside the thing started ripping off electrons from the plexiglass. Okay? So the dielectric strength of plexiglass is 30 million volt per meter, meaning the maximum electric field you can have inside plexiglass is 30 million volt per meter. Any greater and lightning will happen in plexiglass. Okay? You guys understanding this? Yeah. All right, so here the parallel plate capacitor. Okay. Now the capacitance is epsilon naught area divided by D. Okay, so this is with an air-filled one, and if you put a dielectric between them, that's the capacitance. So you want larger and larger capacitance, you could increase the area. You cannot decrease the distance between them too much because the closer they are, the more likely they'll spark. Yeah. Well, anyway, there's a limit to that. Okay, so here's a practical way to do it. So here's a way to make large capacitance. You take a metal sheet, here's a metal sheet, put a piece of paper between them, and roll them up. So here's a compact way of making a large capacitance. Here's another way. So here's metal, and the dielectric is some kind of oil. Okay. High voltage capacitors consist of many interwoven metallic plates immersed in silicon oil. So this configuration can be charged to a high voltage. Okay. Commercial capacitors are often made from metallic foil interlaced with thin sheets of paraffin paper. Now, so, you probably can still buy keyboards like this, but anyway, so keyboards were, okay, so here's a question. So this is a key in your computer. When you press this key, how does the computer know which key did you press? You press an A on your keyboard. How does the computer know you pressed an A? Yeah, so how does it know? Well, okay, so here's the deal. So every key is like this. So, okay, and they're all connected to a 5-volt battery. Okay. So the capacitance is charge divided. Everyone is connected to 5-volt battery. Okay. Now, when you press this key, what happens? D decreases. So D decreases, capacitance increased. Since capacitance increased, it's still 5 volts, but the charge increases. So whatever key you pressed, more charge flow in there. And that's how the computer knows which key you pressed. Okay. Did you guys understand that?
So question.
Mm-hmm.
So each key would have a different number, basically.
No, every key.
Different charge.
Okay, so here are various keys. Every key is connected to a 5-volt battery. You press that key, and if current flows in there, then you know
Oh, okay.
that key was pressed. Mm-hmm. Okay. All right, so this is one of those big boy machines. This is a fusion reactor. It's Sandia National Lab in New Mexico. Okay, so again, what we want to do is we want to do fusion reaction. Okay. On Earth. Do you guys know why we want fusion reaction? Okay, so we talked about fission reaction. Where was my fission reaction? Okay, we'll do fission reaction. Okay, so here's a neutron, uranium-235. This splits into 2 pieces, plus energy is created. Again, this is great, no carbon dioxide, no greenhouse gases, and so this is a green source of energy. Except the problem is a lot of these guys are radioactive for about 25,000 to 100,000 years. Okay. So, I mean, you just have to store it. No global warming and stuff like that. So it's not that big of a problem. But we don't want to deal with that either. You know? This is certainly a better source, in my opinion. You know? So if you take 4 hydrogen nuclei and combine them, okay, now this guy weighs less, okay, and you get energy. Okay, and there's no radioactive debris. This is clean energy, no carbon dioxide emission and no radioactive waste. What is the problem here? How do you see? These guys want to repel each other. They don't want to come close. And to make this helium nucleus, you have to get them within 10 to the minus 15 meters. Why do you have to get them within 10 to the minus 15 meters? The strong force will overwhelm the repulsive force, and you'll form a bound state. How do you get them close? So if you shoot two of them, they'll come this close and then fly apart. You shoot them faster, they'll come closer. Okay? And if you shoot them fast enough, if they come close enough within 10 to the 15 meters, then they'll form a bound state. Okay? So essentially, you'd have to take a bunch of protons and heat the gas up, heat that to a high temperature so they're moving fast enough that when they come together close, when they're coming at each other fast enough, then they'll get close enough and form a bound state. So here's what that national lab will do. They'll use a pellet. They'll shoot lasers at it. All these lasers are fired at the same time for a millionth or a billionth of a second. It will heat this guy up tremendously. So to 2 billion degree Kelvin, for instance, in that example. And then those protons are moving fast enough where some of them will fuse. That's the idea. Okay? And that's the Z machine. Okay? So the Z machine uses a bank of capacitors connected in parallel to store 1,000,000 joules of energy. And the energy is discharged through a target about 1 cc. 1 cc is about this big, literally. Okay? In a few nanoseconds. That's why you needed a capacitor. You discharge that energy in a billionth of a second, which heats this sample up to 2 billion degree Kelvin. Okay? And hopefully some of them will fuse. So we broke even not too long ago, okay, in these machines. Okay. So the power output of the Z machine, so when you discharge that much energy within a nanosecond, the power output of is 100 times the combined power output of all the power plants on Earth. So for a nanosecond, more power was generated than all the power plants on Earth. Now that's a toy. So here's another fusion reaction facility. Okay. So this is the formula for energy stored in a capacitor, 1/2 CV squared. Okay, so you would like larger and larger capacitors to store more and more energy. Okay? Sometimes you can't, well, you know that there's a maximum voltage you can charge any capacitor to. So if you had larger and larger capacitors, you could store more and more energy. Okay? So you like to build large capacitors, and some of them are called supercapacitors and ultracapacitors. Okay? Now for a parallel plate capacitor, here's the value of the capacitance. A is the area of the plates, and D is the distance between them. So to increase the capacitance, you want to try and increase the area. Or decrease the distance, but there's a limit to that. So increasing the area is the strategy. Okay. Now, how do you increase the area? See, well, if you increase the area too large, then packing is a problem. Let's say you want to use it in a car or a bus or something like that. So here's a way to do it. They put activated charcoal, which is fine carbon powder, and the area is effectively the area of all those little particles, surface area of those particles. So that's how you increase the area tremendously. Okay, so here's activated charcoal, activated charcoal. Two layers of activated charcoal are given opposite charges and separated by an insulating material. So that's the dielectric, the red. Yeah. So you increase the area by using fine powder. So this produces a capacitor with capacitance millions of times larger. Okay? And 5 kilofarad capacitor, 5,000, back in the day, 1 farad capacitor was very expensive and very large. And now you can go to Amazon and buy a 5,000 farad capacitor. Okay. So the problem is, however, potential difference of only 2 to 3 volts and energy of 10,000 joules can be stored in these capacitors. Okay, so you can't charge them to high voltage, very high voltage. But this is good enough. The thing about capacitors is, what is good thing about capacitors? Huh? I'm sorry?
It could release the energy at a quick rate.
It can release energy very quickly, okay? So if something can release the energy quickly, it can also be charged quickly. Okay? So that's the deal. So here's a bus that runs on supercapacitors. Okay, and this will work great, and China has this. So here are electrical wires. You stop at a bus stop, by the time people get up and down, the capacitor is charged. Okay? And then you go on to the next stop. And why is this important? No smoke, nothing. So in big cities, in public transports, you can use this. Yeah. Now they've been selling it to other parts of the world as well. Okay. And another thing good about supercapacitors is supercapacitor has a longer lifespan than batteries. Supercapacitors can last between 10 and 20 years, whereas lithium-ion batteries or lead-acid batteries only last about 5 years. Okay? A supercapacitor can also go through 1 million charge cycles, whereas a lead-acid battery, about 1,000 charge cycles and 500 cycles for your lithium-ion battery, for the Tesla. Yep,
What?
that's right.
So would that interfere with any electronics on board of the bus? Or
No,
on board
no,
of the bus?
no.
Okay. So-
Yep.
So what is, when you say 500 charge cycles,
Mm.
what explain that?
So you have a Tesla. Here's your battery. You drive around town, your battery, you discharge it, and then you charge it once. That's one charge. So you get 500 times of recharge. Okay, so
The thing that's really something?
so here's 500 times the recharge, and on each charge you get 300 miles. So you get, that's 150,000 miles, and then you have to replace your battery.
Okay, well, that ain't so wild.
Mm.
No, that's not bad at all, because the car,
I'm driving my car as well. Yeah, my car has 260,000 miles. But replacing the battery is very expensive.